Okay, in the last lesson we learned several new theorems, including the mean value theorem. Today we're going to learn two other quick results that come right from the mean value theorem. Whenever you have quick theorems that come from a big one, they call those corollaries. So you can think of these as corollaries. And once we have all five of them, I think we had three last time and two more today, we'll be able to apply these to all sorts of graphing problems. And so instead of breaking things up and kind of showing each one how each one works individually, I think it's going to be easier to see how they can all be fit in together. So let's first start with a quick review of what the mean value theorem says. It just says if you have yourself some sort of a function that is differentiable, that is, the derivative exists everywhere, and it goes on the interval from a to b, and then you find the average slope of the function between a and b. So in other words, you take f of b minus f of a, that's the change in the y values, all divided by b minus a, that's the change in the x values, that average slope has to occur someplace, assuming it's differentiable. Sounds about right there. There's a point C where the slope at C is equal to the derivative at C is equal to this average slope. So let's see how this is going to be very important in graphing functions. Recall that there's four words that we use when we talk about functions, and here they are. A function is said to be increasing if you have a point A is less than B, if that implies that f of A is less than or equal to f of B. So in other words, this would be an increasing function like this. This would also be an increasing function. It could level off for a while. As long as it never goes downhill, it's said to be increasing. If you want one that never even flattens out, it just always is increasing, then we use the word strictly increasing. Okay, so there, the definition is, if A, this might be A right there, and this might be B right there, A less than B implies that f of A is strictly less than f of B. Okay, so this one always has to be greater than this. It can't even be equal to it. You can guess the other two. Decreasing means that if A is less than B, then f of A is greater than or equal to f of B. So the function might do something like this. Something like that. And then strictly decreasing means that if A is less than B, then f of A is strictly greater than f of B. So something like that. Okay, make sense? So, suppose you have a function where on a particular interval, here's this interval right here, and on this interval, let's say from here to here, you know that the derivative is always greater than or equal to 0. The derivative is always greater than or equal to 0. Can you conclude anything? Well, let's think about it. If you have an A here and a B there, just choose any A or B you want, assuming it's differentiable again, then you can apply this theorem, and you would get what? If you multiply through by this, you're going to get f of B minus f of A is equal to f prime of C times B minus A. But now, if you're told that whatever this C happens to be here, because everywhere here the derivative is positive, or I should say at least non-negative, it's greater than or equal to 0, then look, this thing right here is greater than or equal to 0, this is greater than or equal to 0, and so this whole thing is greater than or equal to 0. So you can bring this over and you get f of B is greater than or equal to f of a. Ho ho. A less than b. F of a is f of a is less than or equal to f of b. F of a is less than or equal to f of b. In other words, this function is increasing. If the derivative everywhere in here is greater than or equal to 0, then on that interval, the function is increasing. Key. What happens if we change it just a little bit? Make it strictly greater than 0. Then this would be positive and this would be positive. So the product of two positive numbers is positive. And so now you bring this over, bring the f of a over, and now you have f of a is strictly less than f of b. F of b is strictly greater than f of a. And so this function is strictly increasing on that whole interval. Okay? Can you see the other two results? If this derivative is less than or equal to 0, then this quantity here would be less than or equal to 0. And so now when you bring the f of a over, you get this. F of a is greater than or equal to f of b. Okay, f of b is less than or equal to f of a. That means the function is doing this sort of jobby. And if strictly less than 0, then this would be strictly less than 0. So would this. And now you have no choice, but the function is strictly decreasing. So that kind of verifies what you might have even told me if I would have just asked you without proving it. That if you have some function, say like this, for example, that from here to here, on this interval here, the slope of the function always looks to be a positive number, and that coincides with the fact that the function is increasing there, whereas from here to here, it looks like the slope of the function at all those points, the slope of the graph is negative, and sure enough, there the function is decreasing. Okay, makes total sense. Okay, but the mean value theorem is what you can use to actually prove it. Okay, so let's put that result in writing. It's that important. So we'll say if f prime of x is greater than or equal to 0, this is on some interval, then f is increasing. If it's strictly greater than 0, then f is strictly increasing. If if the derivative is less than or equal to 0, then f is decreasing. And if the derivative is strictly less than 0, then f is strictly decreasing. Okay, so let's take, for example, a function that we're really familiar with already. Let's just take x squared. Okay, we're going to be applying this to a whole lot of interesting functions later, but just to illustrate, notice what we have here. Here we have f of x is equal to x squared. If we take the derivative, we get 2x. And so sure enough, I just want to know where is this derivative negative. So here I'm interested in the derivative. Where is the derivative negative and where is it positive? So I first ask, where is it 0? Of course, it's 0 right here at 0. For everything less than 0, the derivative is going to be negative. For everything greater than 0, the derivative is going to be positive. So that means that the function is decreasing right here and increasing right there. See that? So sure enough, that's what we already knew, but that all makes sense. Okay? So it's going down until it goes to 0 and starts increasing, going up after you pass 0. Let's apply it to one other function. Let's apply it to the square root. Here you have f of x is equal to the square root of x, which again can be written as x to the 1/2 power. So if you take the derivative, let's see. Take the derivative and you're going to get 1/2 x to the minus 1/2, which is 1 over 2 times the square root of x. Okay, let's put that down a little bit lower. Okay, so here's what we know the square root function looks like. And sure enough, again, see this? For all positive x, this thing here is a positive number. 1 over a positive number is positive. So we know that the derivative is positive all the way through. And sure enough, the function is increasing. Okay, so it makes sense. But I want you to notice something very different, qualitatively different about these two functions. Okay, so I'm gonna I called them both f. Well, that's fine. So they're both increasing. Let's just look at them for positive values of x, just right there. So right here, notice that they're both increasing, but they look very different from each other, right? What's different about them? They're both increasing. There's no asymptote for either of them. Both of them are going to go up, get larger and larger and larger, go off to infinity as you go. But what's different about them? Well, here's what's different. If you were to draw a tangent line to that graph at any place along there, notice that the graph of the function lies above the tangent line. If you were to draw a tangent line to the graph of this function anywhere, notice that the graph of the function lies below the tangent line. See that? That's the key difference. That's the qualitative difference between them. And so we use two more words to define that difference right there. So concave up means the graph lies above the tangent line. I'll just write TL for tangent line. Okay? Concave up. Concave down, as you'd expect, the graph lies below tangent line. Okay, at least on this interval. We're just talking about intervals. You could have graphs like this that vary, or let's just take one like this, for example. See that? It's increasing the whole way, but right here, it lies above the tangent line. It's concave up. Right there, it lies below the tangent line. It's concave down. So the concavity changes someplace in between there. In fact, that place where the concavity changes is called an inflection point. Okay, it's any place where the concavity changes. Inflection point. Okay? So, key word, key difference between two functions. But that raises a question, how can we determine, is there a way to determine whether a graph is going to be concave up or concave down? Of course, I wouldn't have asked the question if I didn't have a good answer for you. So let's see if we can figure out the answer. First of all, let me just make stress a point here that these two things are equivalent to each other. If f is increasing, then this is true. If this is true, then f is increasing. These things go in both directions. It's not like one of those if-then statements where one implies the other. These things are equivalent. They go both ways. So let's look at this function again, x squared, as an example. Let's see what's happening to the slope of this function. Notice that this concave up function right here, concave up, notice that the slope starts at 0 right there. Just kind of watch with me. Here it looks like the slope might be 1/5. Maybe here it's 1/2. Maybe by here the slope is 1. Here the slope is 2, 3 maybe. So what's happening to the slope? The slope is increasing as we go. See that? The reason why this graph is above the tangent line is because whatever slope this is, on the right side of this tangent line, the slope is greater, which means it's pulling this way. And to the left of the tangent line, it wasn't this large yet. So in both cases, the tangent line lies below the graph. And so what we see is that being concave up is equivalent to the derivative increasing. Not only increasing, but strictly increasing. See that? The derivative was strictly increasing. Similarly, to be concave down, let's look at this one. To be concave down, what was happening to the slope there? Here it was actually an infinite slope as you come in towards the origin. And here maybe it's 10, the slope is 10. Here maybe the slope is 4. By this time maybe 2 or 3. By this time it looks like it might be about 1 again. 1/2, 1/3, 1/5, something like that. So notice that the slope, that is the derivative, is strictly decreasing as you go, which again means that graph is going to be below the tangent line. So when it's concave down, that's where the derivative was strictly decreasing. Okay, I guess it was kind of nice to have both of those be F, because I could use both F's right there. Okay, how clever of me. Okay, finally, now let's make use of this. What do I know about any function? I know that if any function is strictly increasing, then, oops, I missed it there. If any function is strictly increasing, then its derivative is positive. Since this function is strictly increasing, that means that its derivative, what is the derivative of this function? The second derivative must be positive. And again, goes both ways. What about if any function is strictly decreasing? If any function is strictly decreasing, what's true about that function? Its derivative is strictly negative. So, since this function right here is strictly decreasing, its derivative, namely f double prime of x, has got to be strictly negative. So there you go. So those, together with these, are the key ideas that we're going to now take and apply to graphing all sorts of functions. And I think we'll probably just stop right here, and then we'll apply all these things in the next lesson to a bunch of various functions. Okay, very good.